Thanks. Okay, so yeah, I'm Ankur. I'm a grad student in the Ant Lab, and I'm also a Spark committer and a maintainer for GraphX, a maintainer. So today I'll be talking about a new project for supporting graph queries in Spark. And this project called GraphFrames sort of occurred to us as a natural extension of GraphX in a couple of different ways. So first, we kind of generally wanted to rewrite GraphX as Spark moved from RDDs to data frames and even data sets. We wanted to rewrite GraphX to take advantage of that. And secondly, we wanted to continue this idea of unification that GraphX started, where it was unifying these relational operations with graph algorithms by integrating graph queries as well in some nice deep way that lets the system optimize across all three of those modes. Okay, so here's kind of a simplified history, first of all, as background of support for graph analysis in Spark. So when Spark was first created, it supported this RDD model, which is sort of a relational or data parallel model that gives you these transformations. And then GraphX in 2013 was introduced to let you express graph algorithms using these relational operators plus some optimizations underneath to make this fast. And now in this talk I'm introducing GraphFrames, which do the same thing but just for graph queries as well. And now overall here we're talking about batch queries that touch the whole graph. So this is separate from what databases like Neo4j provide. Where they support these transactional updates and traversals from a small set of starting points. In contrast, Spark, GraphX, and GraphFrames all kind of focus on this analytical whole graph set of queries. Okay, so first of all, now what's the difference between graph algorithms and graph queries? Well, so graph algorithms are things like PageRank. This is a classic figure that I've used many times in GraphX talks. Like PageRank and alternating least squares. So these are algorithms that are usually expressed as a sequence of steps where vertices pass messages to their neighbors along edges. And in contrast, graph queries are given this small pattern, like here, there's this one with A, B, C, D, E, find all occurrences of it in a graph. So it's known in the theory community as a subgraph isomorphism problem. And of course, as this pattern grows, that becomes hard quickly because, and also the number of possible matches can really increase. But even when you're limited by this kind of constraint to small patterns, this can still actually be a pretty useful primitive, as I'll talk about. Okay, so now I just want to give an example of each to make this very clear. So, here's an example of a graph algorithm, PageRank. PageRank applies to a graph where vertices are web pages and edges are links between them. And the algorithm calculates how important each page is if kind of each link is a vote of importance, and if votes count for more if they're themselves from an important page. So let me just replay this animation where first pages are sending messages to their neighbors, which are these votes, and then the votes are all tallied up, and then the pages that have gotten the most votes grow in importance. And now the overall algorithm proceeds in a sequence of what are called super steps, where after one whole round of this message passing, it starts over, and the new messages kind of are based on the results from the previous iteration. Oh, and also, by the way, what PageRank does ultimately is that it returns this whole graph as where the important thing is this list of importance, where it says, vertex some page like google.com has an importance score of such and such. Okay, so in contrast, here's an example of a graph query, and I'll be using kind of this running example of a Wikipedia data set where there's not only the articles, but also there's kind of the revision history, where vertices are both users and pages, and where the edges are edits. So representing a user editing a page at a certain time. And by the way, that means that each edge needs to have an associated property, which is like the timestamp when it occurred, when that edit occurred. And this kind of a graph that's augmented with properties on the vertices and edges is called a property graph, and that's the sort of format of graph that these systems are operating on. Anyway, so this query, this example query, tries to find users, pairs of users that collaborate often. And here we're just going to define that as editing the same page within the same day. So for example, like here, editor 1 and editor 2 are editing these articles both on the same day. So this is just kind of a really small example of a graph query that you can think of. And sort of the basis is that if these two editors are editing the same page on the same day, maybe there's some real world connection between them. You know, they're discussing the page offline or something. So anyway, we want to find pairs of these kinds of editors that have this relationship. And so this graph query, when run against this Wikipedia graph, will return a table where each row corresponds to kind of a match between this pattern and the actual graph. So that match is just an assignment of these vertices and edges to like actual vertices and edges in the graph. And finally, here's an example of what these look like in code, just to show you what current systems look like. So here's how to express this PageRank message passing algorithm, and this is in GraphX. So GraphX provides this Pregel primitive, which is like this historical name for the format of graph algorithms that does this message passing in rounds. And then Pregel just provides, this is Scala, so it provides these three functions that you can pass in, so the user just defines, well, okay, so when a vertex sends a message, it'll send it to the destination with a certain value, which is the source rank, which is like the reputation of the incoming of the source page times the number of sort of inversely weighted by the number of links that it has, which is the weight on the edge. And then these messages are summed up using a second function, and finally the sums are applied to get the new rank of importance by using this vertex program. That's the third function there. And that's just an exponential weighted function. So, okay, so that's kind of what these graph algorithms look like. In contrast, a graph query is sort of more declarative. And this is the API that the GraphFrames system that I'll be introducing provides. So here, there's this Wikipedia graph that I mentioned, and then all we do is we just express that graph pattern as a string in this cipher-like query language. Cipher is the query language for Neo4j, and then we can also, having done that and having gotten back a table which is a list of matches, we can also run further data frame operations on it, and that turns out to be important to express a lot of these things. So here, for example, I've done this thing where I'm computing the difference between the two dates on each of the edges, and then I'm making sure that the dates don't exceed some amount. So there's this projection, selector, and there's a sort or kind of a filter. Okay, but so why introduce a new system, GraphFrames? Well, currently we actually need separate systems to do each of these tasks. So to run message passing algorithms, there are a bunch of these specialized distributed graph processing algorithms, graph processing systems, which can only run graph algorithms but can't run relational operators or graph queries. So they're highly specialized, aside from GraphX, which was kind of the one that introduced this idea. And then on the other hand, to run graph queries, there are a few of these graph databases that accept queries in a few standard formats. So Cypher is Neo4j's, and then Gremlin is another one that a bunch of databases use. And now most of these do support running relational operations on the results, but they are pretty inefficient for graph algorithms because of the way that the data is laid out in memory. So these two systems kind of support somewhat disjoint sets of things that they can do. Okay, but real graph analysis kind of often involves doing both, right? So here's the same Wikipedia example where we have maybe this raw dump. I actually did this last night. So we have this raw dump of Wikipedia, maybe in XML format, and then we could use we want to use some kind of ETL or like some sort of XML parsing library to extract this into a table where, sorry, this shouldn't be product, that should be article title. So we want to extract kind of the articles, and then turn this into a graph where each article, we've parsed the text of it, gotten the links that, the pages that each article links to, and then we also could take the same data, because these Wikipedia dumps have a lot of information, and then we could take the same data and take it out in a different way. In this case, we can get that same graph that I was talking about earlier, where each user is editing some article at some time. And so then, again, that forms this bipartite edit graph. Okay, but so far, this has all been kind of just relational and graph operations. But now what we can do is run this graph query, where maybe we're doing this query of finding users that collaborate often. And also here's this other example where we could run a graph algorithm, maybe run PageRank and get the importance of each Wikipedia page, and then use that to do this cool thing like maybe finding users who are making these low quality or vandalism edits. So here the idea that I thought of is maybe like shortly after a user edits an article, if another user edits it, then and maybe normalized by the overall edit frequency for the article, then maybe it's like a signal that this edit is a vandalism edit that was reverted quickly. So anyway, the point of all this is that it's easy to think about this kinds of pipelines that involve viewing the same data, the same base data, which is just Wikipedia, in 3 different ways. There's as tables, as graphs on which you can run message passing algorithms, and still as graphs, but where you want to run these kinds of graph queries. Okay, so the solution that I'm introducing today is this system called GraphFrames that combines pattern matching and graph algorithms in a single system and also optimizes across them. So there's this, it has some internals that I'll talk about, and the key thing is it's built on Spark SQL, which makes it very easy to do this and to interoperate with existing Spark code. And the open source release of GraphFrames is announced today. Okay, so here's what the API looks like. Generally, what it tries to do is to unify these 3 models. It's available both in Scala and Python, and it exposes these 3 things. So first of all, there's simple views of the graph as data frames. These are just the constituents of the graph. Secondly, a way to run a graph query and then get the table of results back, as well as to hint to the system that a certain pattern will be used a lot. So here we're saying like maybe you intend to use triangles a lot or 2 or 3 cycles a lot. Then you can hint this to the system and it'll use it in the optimizer. And then finally, it provides a library of common graph algorithms plus a way to write your own. Okay, so here's an overview of how this works, kind of Spark SQL style. So given a graph query string, first of all, GraphFrames parses it. We happen to use a Scala parser combinators library, which is pretty cool. It's very concise. And then it does this translation where it translates this graph query into a relational plan, which is a sequence of joins and other relational operators, so that we can ultimately run it on Spark. Also, if the user registered any views, which are these common subpatterns, then we can look through those and insert those into the plan. And then the idea is that we can save the step of having to recompute them. And also, as I'll mention, these if the appropriate views are registered, then it actually kind of makes it possible for the planner to find plans that it wouldn't have otherwise thought of. So that's kind of an interesting side effect. Next is to apply these custom, slightly graph-specific optimizations to the plan. So there's join elimination. Turns out that duplicate joins are a common problem when generating these kinds of plans, and also join reordering, because the ordering of a join makes a huge impact on the runtime. And then finally, we pass it to Spark SQL to finish optimizing and to run it. So this is the pipeline for graph pattern queries. For graph algorithms, well, the simplest ones can actually go through a similar pipeline, but for now, a lot of the other ones, we actually call out to GraphX and then convert the result back into a data frame. And that lets us reuse the existing algorithms that GraphX has, and lets there be some degree of interoperability here. Okay, so next I'll go into detail on a few of these stages, the ones that are labeled here, those three. So first of all, there's this graph-relational translation. So to give a sense of how graph queries translate into relational operators, let's just give an example. So consider this pattern query where we've actually already matched edges A, B, and C, vertices A, B, and C plus the triangle between them. And now suppose we kind of just want to finish this up by adding the CD edge, adding the vertex D via the CD edge. So to do this is kind of a simple exercise in recursive thinking. So you've already done this. You already have the ABC result. If you want to add CD, well, it's actually pretty simple. So we just take this existing logical plan that has certain output that gives the vertex attributes for A, B, and C plus the edges, and then we just take this and just join in the edge table, where with this constraint that. We take the edge table, join it in such that the source of the edge table is equal to the vertex ID of C. And then we do another join to get the vertex attribute for the new vertex, which is D. And now the result of this is like the finished plan that matches this graph pattern, and that has not only matches it structurally, but also has the appropriate vertex attributes. So kind of here, the overall strategy that we're using is to just generate lots of joins, all the joins that are not logically necessary, and then let them be removed later if the user doesn't need them. So in this case, for example, the user might not really care about the vertex attribute for B. Maybe B is only there just for the structural purpose, not to get the attribute for it. And so in that case, join elimination, which I'll talk about in a few slides, takes care of removing the join that isn't necessary. Okay, next thing is this idea of view selection. So I won't talk too much about the algorithm that goes behind view selection, but rather I'll just motivate why I have views in the first place. Well, so the motivation is that we kind of looked back at GraphX and realized that the key to most of the optimizations there was this concept of the triplet view, and in particular the concept of materializing it. So here the idea is that given the graph as this normalized form, which is where there are these separate vertex and edge tables, that's one way to look at a graph. Another way is to look at it by joining those edges together, those two tables together, where each edge kind of is joined with the attributes of its adjacent vertices. So that joined view is called the triplet view. And that actually it turns out to be useful for a lot of algorithms, so it's nice to expose in the API, but it also leads to some important optimizations. So the way that happens is basically that GraphX internally maintains this join in this denormalized form, and then whenever any updates to the vertices or edges happen, then it maintains that, it incrementally maintains the view. And then that incremental maintenance is kind of where most of the graph optimizations fall out of that kind of maintenance. Okay, so that idea turned out to be core to GraphX, and so we thought we could just generalize this and say, okay, well, the triplet view is just one of the views, but we actually want to support any arbitrary user-defined view, and then use it, maintain it, and apply it to graph queries. And so the idea here is to just take that concept and generalize it from GraphX to GraphFrames. Okay, so that was just the motivation for the views, but there's a bunch of interesting literature on view selection which we're looking into and coding up. Anyway, but on to the next optimization, which is this join elimination that I mentioned. So here the key thing is to avoid joining in the vertex table unnecessarily. And let me give an example of when that would be the case and when we can drop a join and get faster performance. So here's a real example where there's like a small vertex and edge table, and then kind of the standard join that you can't eliminate between these two would be, for example, we can join these two tables, interjoin them and kind of bring the attributes of each vertex into the source of each edge. So this join is an example of something you can't eliminate. But on the other hand, if we just change the the projection there. So like if we just select out only the source and destination and not the vertex attribute, then it turns out that this join, under a certain condition, can be eliminated and can just be replaced with the edges. Which kind of seems like an obvious thing, that, oh, well, we've joined the edges and vertices, and we're only getting back columns from the edge table, so why can't we just drop the vertices? Well, the answer is that in most cases, the inner join is this issue, where you can see that there's this edge at the bottom, there's an edge 2, 5, and there's no 5 in the vertex table, so the inner join is actually going to drop that edge. And so kind of from sort of logically, it's actually not sound to eliminate this join unless we have the constraint of referential integrity between these two tables. And so what we did to get this optimization into GraphFrames was to add a hint kind of to Spark SQL that lets you specify that two tables satisfy referential integrity, or there's actually a different case in the case of a unique key outer join where there's a similar thing where you can eliminate a join. Anyway, so we've taken care of all of this, and it happens at a lower layer. But all GraphFrames now has to do is to indicate that vertices and edges will have this property, and then we can eliminate joins whenever the user doesn't need their results. Okay, I think this is the final slide on optimizations. Now here the idea is that the reordering the join is another key thing. Actually, it's a very difficult problem that databases try to solve, and we attack this with some different set of heuristics. But here I'll again just motivate the idea here. So given this example, slightly complicated graph pattern query. There's an exponential, like, huge number of plans that this can result in, and the reason is that each plan corresponds to one of these join trees, right? So if you give this to a database, this is the plan that you'll just get out by default probably, which is that I mean, if in the absence of any cost-based optimization, you'll get this left deep plan where there's just this just follows the graph-relational translation from earlier, where each edge just gets translated into one join of the edge table and the vertex, the edge table and the previous result. And here I'm omitting the vertex table for simplicity. So it's a whole bunch of joins, and this can be really slow depending on how big the edge table is. Okay, so but it turns out that for this query, there's a much more clever solution for it, which is this bushy plan, so-called. So the idea of a bushy plan is to just do some joins kind of separately, some other joins separately, and then take the results and join them together, rather than maintaining this single big intermediate result that keeps growing and growing. And in this case, not only is this bushy, which is nice, and although it's difficult to find, but also it has this extra very interesting property where this actually has fewer joins than the original. And the reason is that this pattern happens to have this kind of self-similarity where BCD and BCE are isomorphic. So you actually can do that query only once and then reuse the result. That's why there are these two edges here, indicating that there's a self-join going on. And now, as I said, this thing is like really hard to find, and no database will really be able to find it, most likely. But in the idea of GraphFrames is that we can ask the user to recognize the fact that this like kind of triangle structure is something they're using a lot, and if they do that and register that as a view, then the system will be able to take that view and just simply match it against each of the subgraphs in the query, and it'll be able to find this optimization, which kind of through a combination of brute force and user intervention. Sorry, that wasn't intended to happen. Let me just plug back in. Okay, good. Okay, so
Okay, so now finally, that's the most of the talk. I just want to close up with some preliminary results that we've run not on the released version of the code, but on an unreleased version that has a lot more optimizations. And so here I just want to indicate kind of the promise of this approach, that it's actually competitive with real systems. So first thing we did was to compare against Neo4j, which isn't really designed for this kind of a global pattern query. Rather, it's more intended for the case where you have like a single particular vertex that you care about, and then you want some pattern originating from that vertex. So like an obvious example is like in Facebook, they used to have this feature, graph search, where you can find like your friends who are friends with somebody else from from Berkeley and so on, and so that kind of a query is anchored on you. And it makes it easier to solve that kind of query because you can just do a graph traversal that starts with the particular vertex that's yourself. Whereas the kind of unanchored global queries that we're solving are harder, and Neo4j isn't optimized for them, so it's not surprising that we might do better. But the point of this is just to show that on the left side here, there's this anchored query, which is the case that Neo4j is optimized for, and there they do beat us. Not surprising. So this is like just a small graph preliminary results, like I said. But so here Neo4j is doing this thing in like half the time or so that we are doing it, and this is like just simple triangle query on a smallish graph. But on the other hand, for the same query that's not anchored to a certain vertex, but rather is happening on the whole graph. Well, first of all, notice that this is actually a harder problem, and so the scale is different. So it's like tens of seconds up to 60 seconds. So there, we're actually able to outperform Neo4j by like factor of 7 or 6, and that's of course just largely due to Spark SQL's optimizations underneath, but also for more complicated queries, the things that I've talked about in this talk start to apply a lot more. Okay, so here it's just kind of to show this thing solves a problem that systems don't already solve. Next thing is that we're also able to be competitive with GraphX on the territory where it was optimizing for, which is graph algorithms, not graph queries. And so here's this slide. So this is like again a small graph, but it's this per iteration performance on PageRank. And here the idea is that so GraphX used a bunch of techniques to get the to reduce communication, but because it didn't have whole stage code generation that Spark SQL now has in like the Spark 2.0 preview, it still had this hard to avoid JVM overhead. And so kind of just by reusing this engineering effort and without putting too much research effort into it, we're able to already be competitive with GraphX. Okay, and then the final evaluation slide that I have is talking about kind of substantiating this claim that registering the right views can really be good. So this is like a workload from some academic papers of 6 different graph queries that we've run on the same graph as before. And so here you can see that for most of the queries, on the left side there's the results without registering any views. And then on the right thing of each bar is with views. So in most cases it doesn't make it that big of a difference. Although you can see that you can save some time, kind of you can like pull some pre-processing time and make it happen ahead of time. That hopefully the idea is makes it easier to work with the system in an interactive fashion. But the big win happens on queries where there's this structure that can be exploited by the user when they register the appropriate view. And this query 4 is the one that I was talking about earlier in the join reordering slide. So here there's this big performance win because the user has given this domain-specific knowledge that kind of says that there's this sub pattern that you can reuse and get a speed up. Okay, and so it's still very early for the project, but here's a few things that we hope to work on after we've finished working on the initial version of this one. So like one interesting idea is we can actually use some internal data structures here to suggest views automatically rather than asking the user to do that. It won't be as good probably, but it can maybe even tell the user, here are some interesting things that are coming out of your workload. One other really big thing is that these graphs actually have attributes, not just structure. And so exploiting that for partitioning can, and we have some preliminary results showing that it can really be a pretty big win. And then finally, this is a kind of a more general story that we have in Spark, which is that it scales out fine, but then what about scaling down? What about for running the same query on a single node? Can we make this really fast and compete with like the best academic systems that generate GPU code or whatever to do these queries? So that's an interesting problem. Okay, so finally, I'll just leave with this announcement. So there's this preview, open source preview available for Spark 1.4 Plus. It doesn't have all of the stuff that I was talking about in this talk, but those optimizations will come in pretty soon. And we're also going to make a Spark package release in the next week, likely. And thanks to the other Databricks contributors, maybe they may be here. So there's a bunch of people who have worked on this. Yes, and that's my email in case you want to contact me. So I'm happy to take questions.
Awesome. So thank you, Ankur. We're going to have time for about 2 questions. So.
Hi, yeah. So there's some really blatantly obvious question to me. I agree, first and foremost, that graph query is very important, and it seems to be a big missing piece in GraphX. But the blatantly obvious question to me is, why did you base your query language on a proprietary vendor like Neo4j's Cypher and not the W3C standard of Sparkle? Far more powerful, far more appropriate for this, I think.
I see. So question is about like what interface, what's with the choice of interface Cypher rather than some other standards, because there's a Sparkle, there's a Gremlin. So okay, so this I think we don't really see it as a very like key part of the system. It'll be easy enough to support multiple different interfaces. But in this case I think here I just want to point out that this isn't like this isn't full Cypher. This is just like a very small subset of Cypher that's intended to kind of look nice on text and be easy to parse. So it's not as if we've locked ourselves in any way to Neo4j's platform, if that's what you're worried about.
How does it relate to the Maze Runner?
Oh, Maze Runner. So I'm not super familiar with that system actually. Let's follow up offline about that. That'll be interesting. Okay, thanks everybody.